All right, let's go ahead. This is the last thing. It's the only thing that I haven't directly taught you that will be on the exam. And it's math, but don't panic. There are 2 questions like this on the exam. They're worth 4 total points, so it's not that big a deal. But at the same time, this is actually not that difficult. So if you will open your lab books to Avogadro Meets Mr. Mole, on the lab book I have, that's page number 16. But I've learned, especially with the disaster in first hour, I have no idea what page this is actually on. But it's towards the back. Avogadro meets Mr. Mole, and hopefully everyone has that page. If not, there's not a lot of blanks, so just kind of follow along. So here we go. By doing some quick math with the mass of protons, neutrons, and electrons, chemists were able to calculate that 1 mole of atoms contains approximately 6.02 times 10 to the 23 atoms in it. This number, 6.02 times 10 to the 23, is called Avogadro's number. Now you will remember we had a name for this. It was a mole, and a mole meant a big A number. And the whole time we were saying that, I'm sure you were like, what in the world? But it's supposed to eventually help you remember that a mole is Avogadro's number. It's this value. Now, in the lab book last time, we never actually used that number. We talked about it a lot, but we are going to use that number in some calculations in this lab book. And it's super not that bad, I promise. Now, the same thing is true for molecules. There are 6.02 times 10 to the 23 molecules in a mole. Now, if you remember, we said that that big A number, meaning a mole, there could be a mole of really anything. It could be people, sand, cats, or molecules or atoms. Now, these proportions can be written as 6.02 times 10 to the 23rd atoms per 1 mole. And this is a proportion, so you probably know what we're going to do next. And this is the proportion if you're solving for atoms. And it's the same value, just a different word. And if you are asked for molecules, you have this proportion that says for every 1 mole, we have 6.02 times 10 to the 23rd molecules per mole. So that's what you would write in those 2 blanks at the bottom, the bottom of the note section on page 16. Now it's time to apply this using the picket fence. We always, once we find proportions, can use them. And remember, we could flip this if we need to, up or down, and that wouldn't change anything specifically. So here we go. These are the problems right there on the page, so just please follow along with me. It says, how many atoms are in 3 moles of calcium? So if it gives you moles and asks for atoms, this is extremely, extremely easy. It's just like everything we've always done. We need to get rid of moles. So I would put moles down here. And we want to solve for atoms. So I would have atoms up here. And I would just plug in my proportion. Now I've actually, a long time ago, oops, I need to undo that because I erased part of that. I have these already typed, so it was easier. And we would end up with Avogadro's number on top and the 1 mole on bottom. And then we could solve pretty easily. And I don't have my calculator, but I can do this one. We take the number 3 and just multiply it by 6.02. And that will give you 18.06. And then throw that part on the back, well, with the times 10 to the 23rd. And I will take that answer. Technically, it should be 1.806 times 10 to the 24th. That's what your calculator would write. But I would take either answer. I have no problem with either one of those answers. Okay. So will you take a minute and sub, go ahead and pause this. You try number 2 and number 3. Once you're done, compare to your lab partner. Okay, let's go ahead and look how to do these to make sure that you're set. So as always on the picket fence, we take our given. It is 6.5 moles. Whatever unit is here has to come down here. That's moles. Sorry, this 1.8 is so huge. And then we are solving for atoms. So our proportion, once again, is over here. It is that many atoms per 1 mole, or Avogadro's number. So now, and I don't have my calculator, I'm not going to do it, but you would take 6.5 and you would multiply it by 6.02. And I'm just going to pretend, I don't know the answer, but 6 times 6 is 36. So I'm going to add another 3 because it's a half. I'm going to say 39 point, I don't know, 2 times 10 to the 23rd. So you can always just take the number 6.02 times your given and then put times 10 to the 23 as your answer. Now, this one's a little bit different, but math-wise the same. We take my given, 1.8 moles. All right, I need to get rid of moles, so for every 1 mole, I have Avogadro's number of molecules. Nothing really changes. And now I just multiply those two values, and I don't have a calculator again. I'm just going to say that this is roughly 1.8 times 6 is around 12. I'll subtract a little bit and just say 11.5, and then throw that part on, times 10 to the 23. Now when you did it, I'm sure you actually did the math and your answers are a little bit better. Go ahead and check what you did wrong if you have some problems. All right, coming down to numbers 4, 5, 6, and 7. There's another step, but don't worry about it. Uh-oh, I don't know what I just did. I'm sorry. So here we go. Number 4, double check this is the same. How many atoms are in? All right, here we go. It says how many atoms are in 50 grams of sodium. So this does take a little bit more time because we don't give you moles. You have to convert to moles, which we've been doing for a long time, so that shouldn't be that bad. So here we go. You still do the same things, and this is already sort of written, but you take your given 50 grams of sodium and you put it up here. Now, anytime we have a unit in the picket fence on the top, it always goes on the bottom. So I'm going to put grams of Na. And I'm going to find that number on my periodic table. So you'll need that out. If you look, the bigger number in the Na box is 23. I don't know why it changed colors. I'm sure Boatwright enjoyed that. We have 23 grams of Na per every 1 mole of Na, because that's what we always have when we find a number on the periodic table. It's per 1 mole. And then I would have to put moles down here, which is already there, and then Avogadro's number on top. So now I definitely can't do this in my head. I can get close, but you would take 50, multiply it by 6.02, and then divide it by 23. And go ahead and type that in, and you should get some sort of number. I'm going to say it's roughly, I don't know, 12.8 times 10 to the 23rd. That's my guess. This is, I'm sure, not correct. And that would be moles of atoms. Or sorry, that'd be the number of atoms because it asked. Okay, let's do number 5 together, and then I'll let you do the next two. Actually, let's do number 6 together, because it just has a little wiggle that makes it a little bit harder. How many atoms are in 55 kilograms? So really, don't fall for this crap, and I don't do it to you on the test anyway. But convert that to grams. That's 55,000 grams. I don't know why it's changing colors, but whatever. Of fluorine, that's just F. Now I'm going to set up my picket fence, and I'm just going to do the same thing I always do. I'm going to take my unit of grams of fluorine, and if you look at the periodic table, the bigger number for fluorine is 19 grams for every 1 mole. Then I need to get rid of mole, so I put 1 mole on the bottom, and I put Avogadro's number on top, 6.02 times 10 to the 23rd. And this would be atoms, because it asks for atoms right there. And then you do that math. It's 55,000 times 6.02 divided by 19. And I'm not even going to try and guess what that number is. It is some sort of number times 10 to the 23rd. If you're using a calculator that is smarter than just your phones, you will have this that is different, and that's fine. Your answer will be more correct than the ones I'm writing on the board. We're doing it the lazy way. Okay, now let's pause this and you do number 5 and 7 on your own. When you're done, check with your lab partner. So I'll quickly work through these. And once again, I'm not going to type them out as far as answers, but 8.6 grams, I need to get rid of that. That was of BE. So I look at the periodic table, and that's 9 grams of BE for every 1 mole of BE. Then this has to come down. All right, for every 1 mole of BE, I have 6.02 times 10 to the 23rd. This is driving me nuts. Type that in. If you set that up right, I'm sure you have it right. It's almost the same as 6.02. It's probably like 5.8 times 10 to the 23rd or something like that. All right, hopefully that went well. Then the last one down here, I found this value for you. Remember, that's just by adding a CU, 1 S, and 4 O's together. So I have 24 grams of CuSO4. We use this proportion now, 159 grams per 1 mole, 159.5 grams, 1 mole. Then I get Avogadro's number. For every 1 mole, I have 6.02 times 10 to the 23rd. Plug that in, and once again, I can't do this. It's around 1, because 24, 159ths is around 1/6. So I don't know, 1.3, 1.2, I don't know, times 10 to the 23rd. Actually, it'd be 0.01 something. All right, hopefully that went okay for you. What I'd like you to do for the next 10 to 15 minutes is continue this process by doing problems number 67 through 71 on the very back page of your lab book. All of these are exactly the same. If they're given to you in moles, you would just multiply that number by Avogadro's number. If it's given to you in grams, you convert to moles using the picket fence like this, and then you have 6.02 times 10 to the 23rd. The nice thing about these are all of them always end with 6.02 times 10 to the 23rd in the top right corner. So give those a shot. And there are 2 of these on the test. One is straight from moles to atoms. The other one is from grams to atoms. So one of each kind. Hopefully that is good to go.